Okay, so in the winter I'll be teaching a course on splines. The title is Splines and Uses in Computer Graphics. There's actually not a whole lot about using in computer graphics in the course. It's more about splines. So these are our curves and surfaces, and we're mostly looking at polynomials. What spline means are piecewise polynomial surfaces. And a lot of the course is looking at the math behind these things. And a lot of the assignments are taking the math and converting it into code. There are some user interaction topics, but most of the emphasis is on the representation of the curves and surfaces. And so the particular thing we're thinking of using the surfaces for is for geometric design. You want to design objects. So the ship hulls or cars or airplane wings are sort of the classical use for splines. But more recently, with computer animation, these characters have surfaces. They have to get designed and represented in the computer somehow. So these are the applications of these surfaces. And as I said, we look at polynomials, and you're probably familiar with the monomial basis, where you have some x to various powers weighted by coefficients. That form of representation isn't very useful for geometric modeling. As an example of better representation, we have Bezier curves, where we have a set of points, the pi's weighted by Bernstein polynomials, that have this form. And what this gives us is that the coefficients of the basis functions can be treated as points in 2D. And the way that you change the shape of your curve is you move these points around and you get a different shaped curve. And they have a lot of other nice properties that the monomial basis doesn't have. And then we will extend these ideas to surfaces. So in computer graphics, there is this one surface called the teapot that's a bit notorious. This was scanned, manually scanned from a real teapot, but they had non-square pixels and they didn't understand about device independence. So if you go to the computer museum, they have the actual teapot. You'll see it's taller than this one looks because they're pixel stuff. So the surface is up in the top left. And this is a tensor product B-spline surface, and this is the net of control points that were used to define the surface. So then the marking, 6% of your mark will be on homework. And the homework has both theoretical questions and programming, and then 40% on the project. And the project is a project of your choice. Most of the assignments are based on curves. It's a lot easier to work with. And so many of the projects end up being on surfaces. So background, if you have any reasonable undergrad CS background with a bit of math, then that's sufficient. Certainly you would want linear algebra. The main thing that's needed is some level of math sophistication, so that when you see equations, you can look at them and figure them out and don't get scared by a Greek symbol and things like that. And most of the math that we do is geometry, and I will teach that in the class. Often people who have a stronger math background have more troubles with the course because most of modern mathematics is not geometry. You don't have to have a computer graphics background or an HCI background. We give you some sample code that has all you need for the user interface and the drawing so that you can focus on actually working with the curves. So we talk a lot about Bezier curves and B-splines and continuities, how you connect these things up smoothly. Then we extend these ideas to surfaces. And then subdivision surfaces are often what are commonly used for characters in computer animations. We talk some about data fitting and implicit surfaces. The web page is a standard web page for courses at CS at Waterloo. And is there any questions? Okay, thank you.